for almost half a century. Professor Yang has been devoted to 6 major research areas: planetary atmospheres, planetary evolution, atmospheric chemistry, atmospheric radiation, astrobiology, and global change. And he, with a strong emphasis on the interaction and synergy among modeling, laboratory experiments, and field observations, often in collaboration with JPL. He has been involved in many space and Earth missions, such as the Cassini mission and the OCO2 mission. And he also managed an atmospheric observation station in the LA area, which obtained many valuable data on radiation and atmospheric composition. Professor Yang was elected as a fellow of the National Academy of Arts and Science and a fellow of the American Geophysical Union. So today, Professor Yang will be talking about aerosol measurements, radiative modeling, and impact on crop yields. Welcome, Professor Yang.
Thank you, Jing, for this kind introduction. Can you all hear me?
Yeah, your voice is good.
I will talk about this topic, which is on the screen, the aerosol measurements, radiative modeling, and impact on crop yields. These 3 topics are closely related and is the subject of research in my group for many decades. I started working on radiation when I was a graduate student studying with Professor Goody. Most of you probably know my name because my name is on the revised edition of Professor Goody's book on atmospheric radiation. I should add, Professor Goody is 101 years old this year, and he's still active. So this subject is very important today for many reasons. I guess the main reason is what happened the last 2 weeks in Egypt, the COP27. Radiation is important because we are changing the radiation environment, and it has serious impacts on this quality of life on this planet. And then not just on the climate, as I will show, it's also important for the growth of food. What you are seeing is a picture of the LA basin. This is Los Angeles, looking down from the top of the mountain, Mount Wilson. Mount Wilson is 2 kilometers above the surface. And you can see on a typical day, there are a lot of aerosols in the atmosphere. This work is done with large number of collaborators, many of whom are from my group or were from my group. Oh, by the way, if you have any questions, please interrupt, and I will try to answer them as I go along. I will divide my topic into 3 parts. The first part is measurements. And And I will talk about this very special instrument we have on the top of Mount Wilson, right here, like looking down into the Los Angeles basin. We have some very special data. I want to show what this data is like and what we learned from this data. Then I will also talk about radiative modeling, which is a fairly complex subject. But recently we have written a paper which will try to make things simpler and faster. And finally, the main topic today will be to talk about the impact of the aerosols and other pollutants on agriculture, especially the growth of food in the next few decades. So the first topic I will talk about was published a few years ago by my graduate student, Chong. He came from Peking University, got his PhD, and this is part of his PhD research. And this paper was published in JGR a few years ago. So what we have is, I mentioned this data we have from the top of Mount Wilson. We have an instrument that will look at the sun. So here's the sun. We can look at the sun here. The sunlight comes in and hit this plate here. It's called spatula. It's just a white surface. And then it will go into this telescope. But the light can also enter the telescope by looking at by hitting the ground first here. So hit this target and go into the telescope. And then here another target and go into the telescope. So basically, if you now look at this figure, Jing, can you see my pointer?
Yes. Yes.
Oh, okay. Yeah. So basically, so we can look at this the light that directly comes from the sun, or the light that has gone through the atmosphere, go into the surface, hit the surface, and come back. And so we can actually map this whole basin, and we usually divided this basin into 30 different targets, so that we have a very good map of the surface. And then by looking at the sun with this light, we see what is in the clean atmosphere above the boundary layer. LA, Los Angeles, of course, is highly polluted, but above the mountain, the air is much cleaner. So we have some background atmosphere and the atmosphere in the city. Yeah, so here is a simple picture, direct sun, and then light coming to the surface, and then come back here. So this is where the instrument is, and this is the boundary layer, planetary boundary layer, and so we can do this kind of carry out this type of measurements for many years. So the data looks like this. It's a high resolution Fourier transform spectrometer. So from here to here, we have something like 200,000 data points. You see, this is all the rotational transitions are resolved by this instrument. You can see here the major gases like carbon dioxide, carbon monoxide, even some of the isotopes. The isotope carbon-13 CO2, heavy water, HDO, This is in wave numbers, and this is transmission. Transmission 1 means it's top of the atmosphere, and transmission 0 means at the bottom of the atmosphere when the transmission is, when no light can get through. What you see here is the red and the black. It turns out all the red color is due to water vapor. So water vapor, as we know in the spectrum, is everywhere. And then the black are the other gases. For example, the gases like CO2 here. And very important for us, molecular oxygen, O2, here. This is black, but you can still see a little bit of this red. So one of the hard job is to separate our water vapor from the other gases, but we can do it when we have such high resolution. If we don't have high resolution, it will be very hard because now if you mix the black and the red, you cannot separate, and so that's why we need high resolution. Yeah, so this is a typical day when it's clear, looking from the top of the mountain. This is a day when it is not so clear with aerosols, and this is in the morning. In the afternoon, because of traffic and other activities, there are always more aerosols. So you see the atmosphere, and you cannot see the basin. And then sometimes you see nothing. You see, okay, you see nothing because the aerosols completely hit the surface from being seen. So one thing we in the course of measurements was very interesting. We can measure the column because of the scattered light. The light coming back, we can measure the column of CO2 and the column of oxygen, and this line here, this high line here is the looking at the clear sky spectrum that is looking at the sun above the boundary layer, and you see this is what we measure using this instrument for the column of CO2. And this is what we would expect if we just take the geometry, took the geometrical path and multiply by the amount of CO2 in the atmosphere. So you see it falls on this 119. Okay, and the same thing for O2. It should be 1 to 1. But when you look at the light that is coming from the surface. Now you see in the morning it's approximately on this line, but in the afternoon it bend around and it's much lower. You see the measured column of CO2 is much lower than geometric volume. Now you say, oh, maybe the CO2 is changing from morning to afternoon, but look at O2, see even more change. The morning O2 is like this, very much what you would expect on this green line. In the afternoon, the O2 is even lower. And the reason, of course, is due to the aerosol. Because we have high resolution, we can measure the difference between when it is clear and it's not clear, and we can see there are differences, and then it's the difference between the red and the blue. It will be like this, and then we look at the effect of what is we can use the model to compute the effect of the aerosols. And then we can compare with what we can model with what we can measure. So you can see this high resolution data tell us a great deal about the aerosols in the LA basin as a function of time from morning to the afternoon. Yeah, so this is our model. All the green data is from the observations, and all these blue points are from the model, from our radiative transfer model. The same thing. This is for CO2. This is for O2. The same data I showed you before. Now you see we can model it correctly using the effect of the aerosols. And because of that, and because we have this high resolution, we can actually obtain very important information about the aerosols. And then we extended this way after Chong graduated. Zhao Chen came to my group as a postdoc and will continue this work of Zhang Chong. And he is now an assistant professor at Peking University. And he wrote the two very important papers after Chong. One is 2018 and one is 2020, taking advantage of the spectroscopic information, because the spectroscopic information tell us not just that how much aerosol is there, but actually is distribution. And the idea is like this. So we know this light comes from the sun, and then all the other light comes from the hitting the surface. But if you have aerosol, this light cannot reach all the way to the surface. This light could hit this aerosol here and go up there, and hit aerosol here, 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 here. Okay, so it'll tell you where the aerosol is in this vertical layer. Okay, and in this case, you see, we divided the atmosphere into 5 layers. And because we have this high resolution data like this, we can tell the difference. Okay, so the method is known as a scattering and binning method that is published in these 2 papers I mentioned. Now, the LA basin, of course, we know a lot, because we know exactly what the aerosol is doing, and also we know exactly where the aerosol is. Of course, this year we have the total column from some other measurements, but most important is we have LiDAR. We have a LiDAR right here at Caltech, and use the LiDAR, we can get this vertical information. So we have the truth, and therefore we can check our model and see whether this result is correct. Then we wrote another paper, the other paper 2020, where we compare. We use satellite data. Satellite data, we have O2 satellite data from OCO2, which is the carbon dioxide satellite. But the carbon dioxide satellite has the O2 absorption band. So we took this O2, and then we apply this method that can allow us to retrieve 2 variables. One is aerosol optical depth. The other one is aerosol layer height. These 2 pieces of information which I just described earlier. But of course, this year, for the satellite measurements, we need to find out where is the truth. And we use Calypso data as the truth. So So this is our retrieved data, and the Calypso is given by the black. And the same here. This is for total aerosol optical depth. Actually, I think this was done over the ocean region outside of the Sahara Desert. So there's a lot of dust. And then this one is the aerosol layer height. So you notice that it's about 2 to 3 kilometers above the surface. And again, this is the black. The black is the Calypso, which has the vertical information, and the red is using this radiative code with scattering from our modeling and the OCO2 observations. Yeah, so that's what I would say about the aerosol measurements and our attempt to model this vertical distribution. As we know, Cecilia, it's not enough to get just the total aerosol optical depth, which is most of the observations are. For climate effect, for chemical studies, it is very important we also know where the aerosol is, and not just what is the total amount of aerosol. And this method I just described give us this information, and then OCO2 is global. The OCO2 and now OCO3, these two satellite missions that describe measures the mapping of CO2 carries this O2 band. Of course, there's also Tansat from China, also has the same information. And you can see other than the CO2, you can use this information to obtain vertical distribution of aerosols. And of course, OCO2 and OCO3 and Tansat are not the only satellites. There are also about 10 years of GOSAT data from JAXA, that is from the Japan space mission. So extremely variable set of data. I think if we analyze the data, it will be a new revolution in our understanding of aerosols and its vertical distribution. So it's very exciting possibility we have opened up. So the next topic I will address is radiative modeling, which I just mentioned. So I'm showing you a paper that just got published about a week ago. And this is called this two-stream exact single scattering radiative transfer model. So this is called 2SESS. Vijay Natraj was my student. He graduated about 10 years ago. He is now the world's leader in developing this new scattering code, because all this calculation I just showed are extremely expensive, because you have to do thousands of calculations with high resolution spectra. So it's very expensive to compute. And so he developed this new method, which was based on his PhD thesis at Caltech. And this paper just came out. So I will not talk more about it, because everything is inside the paper. There are 4 things I want to point out. This model is general. You can do arbitrary inhomogeneous atmospheres. Second, it can apply to large solar angles or to viewing angles, which is actually very important if you have observations at sunset and sunrise, for example, for remote sensing. This model can go to all those angles. And then the third one, for those of us who have to do remote sensing and do inversion, you must compute Jacobians, and it's very expensive to compute otherwise. other than this method that allows you to compute Jacobian analytically. And then most important of all, this code is an open source. So you can, and here is the website, and you can just download this, and then you can run this code. So I'm not going to tell you how good it is because everything is in. Well, the question you ask is, I think there has been at least 100 papers has been written on two-stream approximation because the radiative transfer equation is just too expensive to solve. So I know about two-stream approximation when I was a student. So there has been at least 100 papers in the last 50 years. The question is what is special about our two-stream method? The difference is very simple. Is that most of the two-stream method are only good to 10–20%, and so you see the red, the dashed line, this dashed line, okay, is the true model. Okay, in this case, we use this model called light dot. It's a full model. Light dot is very much like DSOT for those people who use DSOT. Light dot is almost the same as DSOT. You see the red line is our model. You see the difference is about 1%. So you can barely see it, okay? Now this is the standard two-stream. The reason is that most two-stream are only good to 10–20%. But our method is good to about 1%. So that's why you cannot see different. But if it's like 10–20%, you can see it. And that's not good enough today. It was good enough 50 years ago, but it's no longer. If your model is only good to 10–20%, it's not good enough today. So you have to do better. And that's what we did. This is for all the downward radiance. This is for the upward radiance, the same. You see the red line and the dotted line, you cannot see the difference. But the blue line is from the other standard two-stream model, and you can see the difference. Once you can see the difference, you see it must be like of order of 10%, and that is not acceptable today. So so it was a major discovery by my student when he was working on the thesis, and I finally 10 years later we published this paper. And now everyone can use it to do this multiple scattering for aerosols to address very important problems. One of which is the problem I'm coming to next, and that is the impact of radiation on agriculture. That's not surprising, because growing of food depends on the photosynthesis. And photosynthesis depends on light, and light depends on the scattering in the atmosphere. So this paper published a week ago, so it's hot out of the press, in this journal called The Earth's Future. This is actually a new journal. But this journal is actually quite highly regarded in the field. They told me this journal has an impact factor around 10, okay, which is very unusual for a new journal. And so the question is most of the hardware was done by former graduate student at Caltech, He Li Ying, and then the colleague Jing Wei, but the backbone is Wang Yuan. Wang Yuan used to be research scientist in my group for 8 years. For 6 years. He is now a professor at Purdue University. So he was the backbone of this piece of work, which started off Li Ying was a graduate student at Caltech. So I find a Chinese name for it. 民以食为天. This 天 is very appropriate because this 天 means this sky. You can see this effect of all these aerosols and clouds, effect on the radiation, and the effect of radiation will impact the growth of food. So therefore, this is a problem of really, truly great importance to all the countries, especially to China, which is the a focus of this study, because we not because it's not important in other countries, but because we have the best data that's available for the case of China. Yeah, well, first of all, the effect of pollution on the growth of food has been studied by the biologists for the reason I just explained. 民以食为天. If you are the government, this is your number one job, is to feed the people of the country. And then you have to be worried about what are the factors that affect the growth of food. And so, for example, all those things have been considered. Radiation, temperature, drought, especially in California, where we have a terrible drought for many years, for at least 10 years. And so this water deficit is very important. And then related to that is the soil salinity and pH. And then, of course, it's fertilizers. And then the cold and the heat, insects, pathogens, pollution, and also wind. So the biologists have studied this. So you see all kinds of crops, from almond all the way to grapefruit. Okay, and you can see the effect of ozone and the effect of warming the temperature on the growth of food. And this, of course, again in California, I should say something very special about California. California has just become the world's #4 economy, because previously, California used to be #6 in the world. And California, of course, is the biggest state in the USA. But in terms of economy, it's the #1 in the state of all the states in the USA. So it's like Guangdong. And because it's now the #4 economy in the world, it's like 国中有国, very much like Guangdong. So that's why so many things are done in California, which is way ahead of all the other places in the USA. So that's why we concentrate on the study, a lot of the data done in California. And I will not tell you how California moved from #6 to #2, sorry, to #4, move up 2 steps, because this year, in the last few years, mainly because of politics, because UK divorced with EU. And so the UK, terrible economics. And then Germany used to be #4, but this year Germany was affected by the war between Russia and Ukraine. So the economy of Germany decreased significantly. And that's why California became the world's number 4 after USA, China, Japan. So this is the number 4 economy in the world. So the effect of the aerosols have been studied for many years. I remember it was an extremely dramatic event when the Pinatubo volcano in 1991. Everyone says, well, you have this volcano, you have aerosol, therefore you will see less photosynthesis. The biologists told us it was a great shock to me, especially because I study radiation. They told us the photosynthesis increase because even though the irradiance, that is the direct irradiance, has decreased because of aerosols, the diffused radiation, that is the scattered radiation, has increased. And then the biologist told me the same radiation, the diffused radiation is so much better for the plants than the direct radiation. That's because very simple thing, because the diffused radiation can actually hit the leaf on the side and from underneath, whereas the direct radiation from the sun can only hit the surface directly when it's facing the sun. So if you are in the shade, if there's another leaf above you, you get nothing. But the diffuse radiation is different. As we know, the photons will multiple scatter, and then it can get to you even though you cannot see the sun. This is exactly what happens when you walk on the beach. Even though you wear a hat so that you are protected directly from the sun, but you cannot protect yourself from the light that came off the sand, because the sand is much brighter than the ocean, and then you get sunburn because of the diffuse radiation. So that's exactly for the same reason. So it's a very complicated effect of what happens to the direct radiation, which has been reduced, but this is compensated by this effect of the diffuse radiation that is from the multiple scattering, and that's why it's so hard to do, and that's why so expensive to get all this multiple scattering to be done correctly and fast. So we have some data, for example, from the Central Valley of California, and you can see those. This is the photosynthetically available radiation. And you can see it changes very drastically, mainly because of fires. You see, the fires, you see, this is PM 10 from the aerosol from the fires. And you see the fires obviously affect this radiation drastically. And then the effect of the effect on the use of the light efficiency has been studied, for example, for corn, alfalfa, for example, and then we obtain this kind of data. Now, when you look at this kind of data, it's not impressive. And it was a shock to me because we are used, most of us, especially someone like me, we are used to study the physical data, like light, like rain, like wind. The physical data is actually very quantitative. But when you look at biological data, they're always like this. They're always, because biology is so much more complicated than the study of physical things in the environment. And so that's the challenge. So this team under Yuan developed extremely powerful methods. It turns out when you have data so complicated and very different from the kind of data we are used to, the magic tool today is machine learning, and then so we look at the effect of, for example, the effect of ozone, and this is the impact of the change of air pollution on the crops. There is both the aerosol and the ozone. So here is rice. So rice, of course, is mostly in the southern part of China, and then corn going up to the further north, Dongbei part of China, and then wheat. This is Huabei, Dapingyan, and then this is here is the aerosol, mostly again from pollution, and then it's the ozone again. This is the ozone again obtained from this machine learning study. Yeah, so here is the big picture for the last 35 years, because when for the last 40 years, as you know, 40 years 改革开放, it was a period of exponential growth in the economy, but also the aerosol optical depth. This was the Pinatubo effect I just told you, that the Pinatubo put a lot of aerosols in the atmosphere. This first time I learned something about biology, but that was totally different from what I thought about. Then, of course, China became rich around here, and then they start controlling the environment, especially on the PM 2.5 and PM 10, and so you see it's a drastic improvement of the environment after that. I'm running out of time, so I have to skip some of the statistical approaches. This is actually, in terms of biological data, this is actually very, very impressive. I told you most of the biological data are extremely noisy, not because the measurements are not good, but because biology is so much more complicated than physics and chemistry. So this is what will happen when you increase the AOD. Okay, so the change in the yield, and this is the change of ozone and the change of temperature, and the different colors are for corn, the wheat, and for the rice. You can see they're different. Okay, and even a change of sign, for example, for corn in the change, because corn does not care as much about precipitation, whereas this rice will care a lot more. Rice and wheat will care a lot more about precipitation. Yeah, so here is the chart. Okay, for example, corn cares a lot about aerosol optical depth. And then rice will care a lot more about precipitation. And then wheat cares even more about aerosol. But anyway, this is the whole the impact, the pie chart of all the important factors that will impact the growth of food. And so here would be looking at the picture from the time of the beginning of the modernization in economic modernization in China, and then about middle of the way, you see that drastic change. And then you see then the later stage from this period, current period to the previous decade, the changes are less drastic. But you can see it's the yield of change for the corn and the wheat and the rice. So there is drastic impact from the effect on the historically. So using that to calibrate the model, then we can predict the future. So here is the final thing. I do not want to go through all the details, but the result, most important thing is that the total effect. Okay, total effect, adding up the effect of aerosol, ozone, temperature, and precipitation. And then with the model that has been trained on the data from the last 40 years, we can now predict into the future, like 2050, for example, the total effect for rice. Okay, rice has been pretty much steady, you see, until here, okay, and then it starts decreasing. Here's corn, again, pretty much steady to about 30, 35, and then starts rapidly decreasing. And this one is wheat, same story. It's actually an increase of wheat, you see, and now it starts to decreasing. So the impact of global change, okay, temperature, precipitation, and then pollution, there's from the aerosol optical depth, and then the ozone. Yeah, so this is the conclusion. The conclusion that is we have developed a crop yield model based on this prediction model based on available data. And then during this period, 2010 to 2018, the particular pollution outweighs the negative impact of current climate change. But going into the future, exacerbate global warming will lead to crop yield reduction in spite of the pollution alleviation in the future. And so this is the bottom line, that is there would be a substantial reduction in the food growth based on this model. Yeah, I believe that is all I have. Yeah, so I have to acknowledge my group. Yeah, acknowledge my group. My American students called my group Yok's Army. So I translate that into Chinese. So Chinese into Chinese is the Yulin Jun. Then I noticed that the Yulin Jun may be a simplified Chinese. So I want to translate that into complicated Chinese, the original Chinese 繁体字. And yeah, so this is the Yok's Army in the complicated Chinese characters. Thank you very much.
Okay, thank you so much, Professor Yong, for this great talk.